Okay, so hi, we're going to get started. We're really excited today to present Rose Daly. We're excited because she's an MBA affiliate and she's been working on her master's degree in PFAS, which she'll be talking a bit more now. She's also been helping out a lot in the MONTEVERDE community as a volunteer and doing some awesome work also on water management and other things, as we know that this is a challenge. And thank you.
Hello everyone, thank you for coming to my presentation. Today I'm going to be discussing, like Selena mentioned, my graduate research, which is on PFAS compounds, and these are the toxic chemicals forever in our waters. So briefly, I wanted to tell you a little bit about myself. My name is Rose Daly, and I'm currently a student at Michigan Tech University pursuing a master's degree in environmental engineering. So I've been living in Monteverde for the past almost 4 months now, but my home is Michigan in the United States. And I grew up in Detroit, which is in the bottom right corner of Michigan, but the funny thing is my school is actually about as far north as you can go in Michigan. So way up in Lake Superior in the Keweenaw. That's where I go to school. We are so far north, we have about 9 months of cold weather and snow. So it's been very nice living down here in Costa Rica. It's a really good change of climate. And the funny thing is, Michigan Tech is actually the snowiest campus in the United States. So we get over 5 meters of snow annually. My two passions are aquatic chemistry and sustainability. So all of my graduate studies through Michigan Tech are focused on aquatic chemistry, specifically the PFAS chemicals. However, I also love sustainability, so I'm really happy I have this research affiliation here at Monteverde Institute because I'm able to work on sustainability projects in the community, such as designing constructed wetlands for local schools to treat gray water. But today, my presentation will be focused on the aquatic chemistry side. I know chemistry can be intimidating sometimes, but I'm going to make sure my presentation is as understandable as possible. I want everyone here today to fully understand the PFAS issue and what we researchers are doing to try to resolve this issue. All right, so I want to start with some background information on the PFAS compounds. PFAS stands for per and polyfluoroalkyl substances. I have two shown right here on the screen. We have PFOA, which is up at the top, and then we have PFOS down here. These are two of the most common PFAS chemicals that you will find in products and also in nature. Now, if we look at the name of PFAS, we see the word polyfluoro, so that means many fluorines. If you look at these chemicals, you will see a lot of yellow and then green balls or atoms. These represent fluorines. So these compounds are characteristic of having many, many fluorine atoms in them. If you ever look in the news, you may see these compounds classified as forever chemicals. We will talk more today about why they're classified as the forever chemicals, but it's not a good thing. So the company that's responsible for producing PFAS chemicals is DuPont. And they started making these compounds back in the 1940s. And what they wanted to do was they wanted to make a really unique compound that was resistant to fire, water, and grease. So that is how the PFAS chemicals were born. They're this unique class of compounds that can resist water, they can resist fire, grease, and many other surfactants. So because of these unique properties of PFAS compounds, we actually see them in a lot of products that we use every day. The most common use for PFAS is firefighting foam. So of course, having a chemical that's resistant to fire, firefighting foam is the perfect application for this compound. Additionally, a lot of PFAS compounds are used in fast food packaging. So I don't know if you guys have ever gotten fries from McDonald's or like a burger from Burger King, but they always come in little cardboard containers. And you'll notice the grease never seeps through the cardboard. That's because these cardboard containers are lined with PFAS, which are grease resistant. So they hold the grease inside the cardboard, and then you don't see the grease stains on your containers. A lot of us probably use non-stick pots and pans. They're non-stick because they're covered in PFAS chemicals, which are resisting oil and grease. This makes our lives super easy because we can easily clean these pots and pans without scrubbing them for hours. PFAS is also water resistant, so we'll see a lot of PFAS. In the US, a lot of people will have carpeting in their homes, and a lot of times carpeting will be stain resistant. That way if you spill a drink on it or your pet, like, I don't know, throws up on your carpet, you can easily clean that away because your carpet has PFAS in it, creating that layer that will just keep all the liquids out of your carpet. So as you can see, PFAS are used in so many different products. I can't even talk about all of them today. They're also in electronics, they're in pesticides. But by a show of hands, how many of you have used one of these PFAS products at least once in your life? Probably all of us, because they're so common. And because they have so many unique applications, there's actually over 4,500 different types of PFAS. And as you can see, looking at all these compounds, they all look a little bit different, but they all share the same common characteristic of having a lot of those fluorine atoms on them. And those are really what make the PFAS what they are. So the question is, PFAS makes our lives really easy. We can put out fires with PFAS. We can have really easy cookware to clean with PFAS. I can stay dry with my PFAS. So what is the issue with our PFAS compounds? And the main issue is, we've been using these products since they've been in production, so since 1940. So we've had about 80 years of using these products. And what happened is, over time, we're eventually also disposing of these products, right? We're using, we're eating our fast food, we're throwing the packaging in the trash, we're putting out fires, and eventually that foam is making its way into the environment. So what has happened is, through use and disposal, PFAS have entered our environment over the past 80 years. PFAS have entered our waterways. So a prime example of that is when you're putting out a fire, the foam doesn't just disappear, it has to go somewhere. Typically it's going to run into the sewers, or if there's a body of water nearby, it's going to run into that body of water. So here we can see an example of PFAS firefighting foam filling up this lake right here. So that is how we get direct PFAS into our environment. We also see PFAS in our soil and groundwater. So a lot of these products we end up putting in the landfill. So we have fast food packaging, we have cosmetics that have PFAS in them. Maybe we have like a really old raincoat that doesn't keep us dry anymore. And eventually all these products end up in the landfill. Now people tend to think that items in the landfill stay in the landfill. Like once it's in there, it's sealed up and it can't get out. But the truth is, chemicals tend to leach out of the landfill. So what you see here is you'll see our pile of trash in the landfill. And then we have a leachate pond. So there's going to be chemicals that are leaching out of the products in the landfill. And these are going to form a little pond. So landfill designers do account for this leachate. And they typically put down a liner to keep all of that chemical liquid in one area. But that liner is not perfect, and over time that leachate is going to percolate down through that liner, and it's going to enter the groundwater and the soil and eventually make its way into surface water. So even though things are in the landfill, they're not there forever. The PFAS is still going to get out and get into our environment. Lastly, we also see PFAS in the air. So PFAS are actually still being produced today because they are in so many different products. And these companies producing PFAS, they of course are going to have emissions. And these emissions are containing PFAS, of course, and they're going to leave their manufacturing site and enter the air. And then that might get into our rainwater, get into our groundwater, etc. So we have PFAS in the air, in the water, and in the soil. So my question for you is, do you think PFAS break down naturally in our environment? Okay, so everyone's shaking their head no, and you guys are correct. If they did break down naturally, I would not be here today presenting to you. So yes, PFAS will not break down naturally in our environment. And that's because they're, first of all, man-made chemicals, but also they're resistant to water, they're resistant to fire, they're resistant to grease and oil. So everything in our environment is not able to break these down. UV light from the sun will not break these down. Bacteria and microbes cannot break these down. These chemicals are just building up in our environment, and they're just accumulating. And as a reminder, we've had these in use for 80 years. So we have 80 years worth of PFAS accumulating in our environment. Now, to better understand why these won't break down in the environment, let's actually look deeper into the functional chemistry of the PFAS. So as a reminder, this is our PFOA compound. And here's the chemical formula right here. We have a carbon backbone. We have our fluorines, which are the yellow balls. And then we have a carboxylic acid functional group here. So we have 2 oxygens and a hydrogen. This is the chemical makeup of PFOA. Down here in the corner, you will see water or H2O. Now, you don't have to have any chemistry knowledge to answer this question, but I want you guys just to make some observations about PFOA. What do you see about this compound? What things do you notice about it?
It has a lot of fluorine.
Yep, it has a ton of fluorine. We have a total of 15 fluorines on this compound, and that is very unusual for a chemical. They usually do not have that much fluorine. What else do we notice?
It's very big.
Yeah, it's a very big molecule. Compared to water, water is 3 atoms. This compound is, I don't even know, 20, 30 atoms in this compound, so it's very, very large. Anything else we notice about it?
It's got a central carbon in it.
Yeah, we've got that carbon backbone. Any other thoughts from the audience? So a couple other things is this is a linear compound. So we have aliphatic, which is linear, and we have aromatic, which are round. This is a linear compound. That's going to be important. And then also, we see a really big carbon-fluorine chain, and then we just see this little unique functional group. So we have 2 very different parts of this compound chemically. We have carboxylic acid, and we have our carbon fluorines. So to summarize, we identify these 4 characteristics. It's really big, lots of fluorines, it's linear, and it has that unique functional group, or that carboxylic acid. So now that we've identified these properties, what do these mean? Now the first 3 are actually really important because what they tell us is the bond strength of this compound. So as we pointed out, we have a lot of carbon-fluorine bonds. Now compared to carbon-hydrogen, carbon-fluorine is actually 200 kilojoules per mole stronger than carbon-hydrogen. And this actually makes carbon-fluorine one of the strongest bonds in chemistry. So it is very, very difficult to break a carbon-fluorine bond. Now it makes more sense why these can't be broken down in the environment, right? And then let's talk about that unique functional group. So we have 2 different parts of our compound. We have a hydrophilic side. Hydrophilic means water-loving. And then we have a hydrophobic side, which is the carbon-fluorine chain, which is water-repelling. So we have 2 drastically different sides here. We have a water-loving side and a water-repelling side. And that's what makes these compounds so effective at being surfactants. So we have this side, which will latch on to any surface, and then we have this side, which will repel water or repel fire, depending on the structure of the chemical. So that's also really important to know, is the 2 different sides of this compound. So now that we've talked about the functional chemistry, and we know these are accumulating in our environment, why should we be concerned? And there's 4 main reasons why: mobility, persistence, bioaccumulation, and toxicity. I'm going to cover each of these right now. So first, let's talk about mobility. So I know in the US, we use PFAS products. I also know they use PFAS products over in the Middle East and China, in Europe. I think in Costa Rica, we use a little bit of PFAS here. I'm not too sure about the other areas of the world. I think they might use PFAS. But PFAS isn't used everywhere. For example, it's not used in Antarctica. They don't have firefighting foam down there. No one lives down there really, so they don't have all these products that have PFAS. Same with areas like northern Greenland. But what researchers have found is they've actually measured PFAS concentrations as far south as Antarctica at 10 picograms per cubic meter. What this tells us is PFAS can easily travel through the air and through the water. So that is how PFAS ended up in Antarctica. So really, there's nowhere safe in the world for us. There's PFAS everywhere just because of how mobile it is. It can easily flow through the water and travel through air. Now this map is a little bit difficult to see, but what this shows us is the concentrations of PFOA and PFOS at different parts of the world. So we see really high concentrations in the USA, over here in China, in Switzerland, and in some other parts of the world as well. So PFAS is everywhere, whether we want it to be or not. So now that we know PFAS is mobile, let's talk about persistence. So what I mean by persistence is that PFAS build up. They don't go anywhere. They keep building up and accumulating. So looking at the United States, we can see 3 main areas where PFAS are building up. We see military sites in purple, drinking water sites in blue, and then other known sites in red. So that might be in your lakes or your streams. So a question for you, why do you think we see such high PFAS concentrations at military sites? What are they using at the military sites?
The foam?
Yeah, the firefighting foam. They do a lot of training exercises at these sites with firefighting foam. So that is why we see such high concentrations at these military sites. Now let's look specifically at Michigan. We actually have a very big PFAS issue in Michigan. And we even have PFAS as far north as my school, Michigan Tech, so that's really unfortunate. But we in Michigan are very, very concerned about the PFAS issue because we have our 5 Great Lakes. So we want to do everything in our power to get the PFAS out of our beautiful lakes. All right, so now let's move on to bioaccumulation. So what bioaccumulation means is that as this compound moves up the food chain, it's going to increase in concentration. So if we start here with our suspended solids, and then down here to our microplastics and our microbes, we're going to see really small concentrations of PFAS. So about 3.9 picograms per milliliter. However, as those microplastics are digested by microbes and then again by collectors, and then again by these fish, we see those concentrations jump up to about 14 nanograms per gram. And then eventually these little fish are eaten by the big fish, so the concentration has grown even more to about 60, and then we humans eat this fish. So bioaccumulation is something that's so dangerous when it comes to contaminants because we don't even know how much we're eating because it just keeps accumulating up the food chain. All right, now let's talk about exposure. How are we humans primarily exposed to PFAS? We can inhale it through the air. We could have skin contact with it, so we could touch a PFAS object and it could enter our skin that way. Or we can ingest it through eating and drinking. But the primary exposure route for humans is ingestion. So we're either drinking water that has PFAS in it, or we're eating food such as fast food and that cardboard that has PFAS on it. Now, what happens to us with regards to our health? So we actually can see a lot of detrimental health impacts of PFAS. PFAS is a known carcinogen, so it's causing cancer in us. It also affects our reproductive organs and our hormones. We can have a suppressed immune response, meaning we're more susceptible to diseases. And then lastly, we could also have some thyroid issues. And this is just a short list. There's a lot of other health impacts just from digesting the PFAS compounds. Okay, so we know how it can affect us, we know how we're exposed to it, but how toxic is this compound? And I don't actually have an answer for you. The toxicity of these compounds are largely unknown. There's very limited human data with these compounds. However, people have been doing experiments with lab rats to see how much the lab rats can ingest before they start growing cancerous tumors or before they die. So here's the first study, which is acute or single exposure. So what this means is they give rats a single exposure of PFAS. They give them 1 drop of water that has PFAS in it, or they have 1 bite of food that has PFAS in it. That's an acute exposure. And what we have here is the LD50. Does anyone know what the LD50 is or what it stands for? So LD50 is the lethal dose required to kill 50% of the population. So if they have 20 rats, if they give them this concentration of PFOA, that will result in 10 of the rats dying. That's the lethal dose 50. That's typically how we measure acute exposure. So they did this for both PFOA and PFOS, and it's going to be about 500 milligrams per kilogram of body weight that the rats have to ingest in order to die from a single exposure. Now, this is a really high number, so we don't have to be concerned about being acutely exposed to PFAS in this manner. However, they also did a chronic exposure. So this is where they continuously expose rats to a small concentration over the course of a certain amount of days, months, or years. So in this study, they did a 90-day study where every day they exposed the rats to either 0, 2, 6, 18, all the way up to 200 milligrams per kilogram of body weight per day. So every day the rat was exposed to 2 milligrams. And what they found is anything between 1 and 6 milligrams per kilogram of body weight resulted in increased liver weight, so that's showing a serious issue. And then anything above 18 resulted in death of the rats over 90 days. So as you can see, PFAS compounds are very toxic. We don't know fully how they affect humans, but we know for a fact that they can be very deadly to rats and other animals. So to summarize what we've talked about so far, PFAS are toxic to humans and animals. They negatively impact our health and likely cause cancer. They have spread globally. We know they bioaccumulate and persist in our environment. And they do not naturally break down. So now the big question is, are the PFAS compounds regulated? Is our government in the US, in Costa Rica, all over the world, what is the government doing to regulate these toxic compounds? Are they doing anything to help protect ourselves from ingesting contaminated water? And the answer is yes and no. And for this, I'm going to focus on the United States. I wasn't able to find any PFAS regulations for Costa Rica, but we'll talk about what's happening in the US. So what the US has is we have a lifetime health advisory, or an LHA, and we have a maximum contaminant level, or an MCL. Now looking at both of these, the difference between them is one is enforceable. So what that means is if the government catches a manufacturing site emitting more PFAS than that level, then they can fine them or shut them down. Now the other one is not enforceable, which means the government can say, you should keep your PFAS emissions below this level, but if you go above it, they can't do anything about it. So which do you think is which? Which one's enforceable, which one is not enforceable? Any thoughts? Any guesses?
Well, wouldn't the LHA, the Lifetime Health Advisory, be more enforceable?
So this one actually is not enforceable. It's an advisory. So the government advises companies, manufacturers to stay below that limit with their emissions, but they can't enforce it. It's the maximum contaminant level, which is enforceable. Now let's talk about where these are in the US. So Michigan has MCLs for PFAS, so that's great for Michigan, but the rest of the US, they just have a lifetime health advisory. So the EPA, or Environmental Protection Agency, they're trying to slowly make changes, but right now nothing is enforceable. But Michigan has taken it upon itself to make strict rules for these manufacturers so we can protect our environment. Now, what do these levels look like? In Michigan, we regulate a total of 7 PFAS compounds. You can see the 2 most common ones are in our list. We have PFOA and we have PFOS. And these are the concentrations. Everything here is shown in PPT, or parts per trillion. You can see we have drastic ranges here, all the way from 6 up to 400,000 ppt. Now, the rest of the US has set a 70 ppb advisory level, but again, that's not enforceable. So can anyone explain to me what a part per trillion is? Because it's so important for us to be able to visualize how much is a part per trillion? How much is 8 ppt? Is that like a glass of water? Is that like a lake? Does anyone know what a part per trillion is? Any guesses? Okay, so a PPT is 1 part per trillion. If we have 1 trillion marbles, one of those marbles is going to be a PFAS marble. So 1 out of 1 trillion is of concern. So here we have 6 ppt, 8 ppt, but marbles don't really help us visualize PFAS because it's an aqueous contaminant. So let's think in terms of water. This right here is an Olympic-sized swimming pool. I'm sure everyone's familiar with how big this pool is. You've seen the Olympics? Okay, so this has about 2,500 cubic meters of water in it, or 660,000 gallons. Now, let's actually envision not 1 Olympic swimming pool, but 20 Olympic swimming pools. Okay, so now we have 20 Olympic swimming pools. So someone can do the math, but I think is it 50,000 cubic meters of water? So if we add 1 drop of water to the 20 swimming pools, that is 1 part per trillion. Like, that is such a small amount. So basically, to fill up 20 swimming pools, you need 1 trillion drops of water, and then if one of those drops is PFAS, you're already at the 1 ppt limit. So we saw limits at 8 ppt. So that's 8 small drops of water in this much water. Like, that's insane. But the government, in Michigan at least, is doing everything we can to keep these levels as low as possible. Because anything above those MCLs, or maximum contaminant levels, can cause toxic effects in humans. All right, so the next question is, PFAS is regulated in some areas, but we know it's bad for us. Is there any way we can get PFAS out of the water? And luckily the answer is yes, we can remove PFAS from the water. There's a lot of technologies out there that are designed to remove PFAS from water. The most common one is granular activated carbon, or GAC. So this is what granular activated carbon looks like. It's just little pieces of activated carbon. And what treatment centers are doing is they actually create a bed of GAC, and they run water through that bed. And then what happens is the carbon will actually adsorb the PFAS, and then the water is cleaned and passes on to the next segment of treatment. Now, the reason this is so effective is because of the surface area of the GAC. So this is a microscopic image of GAC, and these are very, very porous. They have a ton of tiny pores on their surface, which makes them have a huge surface area. If you really think about the pore space in this compound, they have a big surface area. And what happens is that hydrophilic side, so the water-loving side of the PFAS, will actually adsorb to these pores. And that is how the PFAS is taken out of the water. So this is a really great technology. And what they found, okay, actually I don't have a number on this, but there's actually a shortcoming of this technology. So can anyone think of what the issue might be with this technology that takes PFAS out of the water? Really think about it. Why might this actually be not the solution we're looking for? Selena.
Well, doesn't the PFAS stay inside the carbon?
Yep. So the PFAS is removed from the water, but then we have carbon that's full of PFAS. And what do you think we do with this GAC that's full of PFAS? Any thoughts on what water treatment plants do with this?
Put it in the landfill?
Yeah, we can put it in the landfill, or there's one other thing they do with it. Not compost. Paul?
Burn it.
Yeah, we incinerate it. So we have 2 things we do with GAC. We either incinerate it or we landfill it. And we know with incineration, the PFAS is going to re-enter the air. And with the landfill, over time, the PFAS is going to leach through that liner, like we talked about, and enter the groundwater and the soil. So GAC is a quick fix for PFAS, but this is not the answer. What we really need is a method that will fully destroy the PFAS compounds into non-harmful byproducts. This is where my research comes in. So now I'm going to switch gears to talking more about what I am doing as a researcher to destroy the PFAS compounds. So the technology I'm looking at for destroying PFAS compounds is advanced reduction process ultraviolet technology. So what you see here is a tank of water that has a UV light inside. This is the technology we can use to destroy the PFAS. So ultraviolet light has the ability to excite certain compounds, and when they're excited, they can produce certain radicals, which are really reactive and can destroy contaminants. So what happens here is you're going to fill up your tank with your PFAS-contaminated water. Then you're going to add a compound that the UV light can excite. So in this case, we're adding a salt of sodium sulfite. Now what happens is when we turn on the UV light is going to excite the sodium sulfite and produce solvated electrons. So that's going to be a single electron produced, which can then go on to attack the PFAS compounds. Now, if you look at reaction rates down here, so K is how quickly the electron will break down a contaminant. We see reaction rates on the order of 10 to the 10th molarity seconds inverted. So that's a really fast reaction that's happening. Why do you think these single electrons are so reactive? We have to think back to chemistry class. Why is a single electron so reactive? Okay, question for you. Inside chemical orbitals, are electrons usually paired together or are they by themselves?
By themselves.
They're not usually by themselves. They're actually usually paired together and they spin in opposite directions. So in every orbital, there's 2 electrons. Now, when they're together, they're really stable. When you take one away and you have a single electron, it just goes crazy. It's so energetic. So that is why having these single electrons attack the PFAS is such a great destruction technology. Now, research has shown that PFAS can be broken down fully to a concentration of 0 using this technology, and in the course of just 6 to 12 hours, we can destroy the PFAS fully. So this is such a great technology for us. Now, there are 2 challenges that come along with this technology. You know, it's not as easy as just setting up these photoreactors and destroying the PFAS. The first challenge is, will this method effectively destroy the 4,500 different types of PFAS? Just because UV ARP can destroy one type of PFAS does not mean it can destroy all of them because of how different they are. They all have those uniquely different functional groups. So that's challenge number 1. Can this destroy all of them? Challenge number 2, what byproducts will be produced? So as the electron is tearing apart the PFAS, what's happening to it? Is it producing CO2 and fluorine gas? It'd be great if it did. These are non-harmful byproducts that we can easily deal with. Or is it actually just tearing off one CF group and just creating a smaller chain PFAS? So these are 2 really, really important challenges and questions we have to ask when we're looking at a destruction technology. So what I'm doing for my research is I'm looking at destroying the PFAS with the solvated electron. I have 2 main goals for my research. Goal number 1, and this relates to challenge number 1. I want to be able to predict the reactivity of the PFAS compounds so we can prioritize them for this destruction. So basically, I want to figure out how reactive is this compound with the electron versus this compound. If they're not reactive, then this is not a good technology. If they are reactive, then yes, let's go through with this technology. Goal number 2 is I want to actually figure out how the electron breaks these down. Are we going to create shorter chain PFAS, or are we going to fully break them down into CO2 and fluorine? These are my 2 research goals. So now let's start with the first goal. How can we predict the reactivities of the PFAS with the electron? There's 2 different methods we can use to predict reactivities. The first method is we can perform experiments. So what we can do is we can put one type of PFAS in our photoreactor with the electron and measure how long it takes for that compound to break down. Then when that's done, we can add another type of PFAS, and another one, and another one, and we can keep running experiments to measure that reactivity. Or we can use highly accurate computational methods. So we can use software that can simulate these reactions, and they can do the reaction and the measurement in a fraction of the time. So which of these methods do you think makes the most sense? Method 1, method 2.
Number 2.
Okay, I think everyone's saying method 2. You guys are absolutely right. If we were doing experiments, it would take us years and years and years, and it would cost us so much money to keep ordering PFAS samples and to keep running our UV light. So method 2, doing everything computationally, is what makes the most sense. And luckily in this day and age, we have extremely intelligent software we can use to predict these reactivities. So I actually do a lot of computational chemistry work, which is why I was able to travel to Costa Rica to continue my work, because all I need is my laptop and I will be good to go. So what I do is I work on the Michigan Tech supercomputers, which have over 2,000 processors to run my simulations. And what I do is I build PFAS molecules in a software called Gaussian, and I'm able to optimize them or bring them to their lowest energy state. And then once I have the compound optimized, I can then predict its reactivity with the solvated electron. Now, how do we predict reactivity? That's the question. Like, how do you do that on a computer? So there's one thing I'm measuring in each of these compounds, and that is the one electron reduction potential. So we all know about reduction potentials, right, from chemistry class. We can either oxidize a compound or we can reduce a compound. Oxidize is losing an electron. Reduction is gaining an electron. So of course, if we're using an electron to attack PFAS, that's reduction, right? So if I measure reduction potential using my software, then I can use that to eventually predict reactivity. So what I was able to do is I was able to look at different classes of PFAS compounds. So the class that has a carboxylate functional group, the class that has the phosphonate functional group, and I was able to estimate the reactivity using my software. So on the, or excuse me, not the reactivity, the one electron reduction potential. So if you look here on the y-axis, you will see the reduction potential ranges for the different classes of PFAS compounds. And once I have reduction potential, I then can estimate reactivity. So reduction potential is represented by this E here. That is the reduction potential you see on the y-axis. And then K-chem, that's reactivity. So I can use a simple linear free energy relationship, or LFER, to predict that reactivity. So then what I did is I created my LFER charts. On the x-axis, we have that reduction potential, and then on my y-axis, we have reactivity with the electron. So as you can see here, I've developed two relationships we can use to estimate the reactivity of the PFAS. So this is really useful because if we find a new PFAS in nature, if we're able to measure that reduction potential, we can then plug it into this equation and predict how reactive it's going to be with our technology. So this was the first part of my research, was creating linear free energy relationships based on different reduction mechanisms. Now I'm actually taking this a step further, because what if we can't calculate the PFAS's reduction potential? What if it takes too long? What if it's too expensive to measure in the lab? We need a better solution to be able to predict reactivity where it doesn't require us to go in the lab or to spend hours on the supercomputer. So currently I'm actually working on building a group contract GCM using Fortran software. Now Fortran, you might have heard of this. NASA uses this coding language a lot for their spacecrafts. But I'm currently using Fortran to build a GCM. Now what a GCM does is it actually looks at the chemical structure, and based on the structure, we can predict the reactivity. So this is a great, in nature, if we detect a PFAS, we know what its structure is, right? We can see that structure using different technologies like mass spectrometry. So let's use this phosphonate as an example. we see that unique. This time it has phosphorus and then alcohol, and then we have that same carbon-fluorine chain. So what I did is I fragment the structure of the compound. So when I say fragment, I break it into pieces based on what's similar. So we have one phosphonate group in the whole compound. So we have one of those. We also see CF2s, so these little cross points. So we see a lot of CF2s. And then on the end, we have our terminal group, or our CF3 group. So these are the three different structural fragments we see in this compound. So then if I multiply the number of CF2s, because there's more than one, I can actually set up this relationship here. So I can say reactivity equals the phosphonate times CF2 to the 9th power times CF3. And for each of these, I've assigned a Y parameter in my code. So what this can tell us is, as long as we know the structure, then we know how quickly it will break down when it's exposed to the solvated electron. Okay, so that is the research goal number 1. Now moving on to number 2. How can we figure out what this is going to break down into? Is it going to be CO2 and fluorine gas, or is it going to be another PFAS compound that's shorter in size? So what I'm doing is I'm actually, so again we have our reduction potentials that I was looking at earlier, and I'm actually calculating the reduction potential for all possible attacking sites. So does my electron attack this carbon? Does it attack the carbon back here? Does it attack that middle carbon? We don't know. So what I'm trying to do is I'm calculating the reduction potential for each of those attacking sites, 1, 2, 3, 4, and 5. And what I found is we usually see a reduction potential that's significantly different than the rest. So in this case, position 1, so the functional group right here, is the location where the electron is going to attack this compound. So this lets me know that it's going to associate with that carbonyl functional group, and that's going to give me insight into how it's going to break down the rest of the compound. All right, so now what I'm able to do is look at potential energy surfaces for each of those locations. So now in my software, I'm actually separating those bonds. So I'm saying, okay, if the electron attacks right here, it's going to tear off that CO2 group. Versus if it attacks back here, it's just going to pull off of fluorine. So I'm measuring potential energy surfaces in the superconductor. I'm actually able to predict potential energy, or the energy required to break that bond. And this will tell us which bond will break first, which one will break second, etc. And then we can see how this compound will break down. And from there, I can start developing reaction mechanisms, which will tell us what the end products are going to be. This is currently in progress, so I don't have any results on this right now. So in summary for what we talked about today, we know that PFAS are used in a large amount of products, in our raincoats, in our fast food packaging. We also know that there's over 4,500 different types of PFAS compounds. They're such a big contaminant. We also learned that PFAS do not break down naturally, and they are accumulating in our environment. There is no way they're going to naturally break down over time. We've also learned they're toxic and they cause cancer in humans and animals. We also learned that most PFAS are not regulated by the government, although regulations are in the works right now. And lastly, we learned that the need is to find a destruction technology for these PFAS. That's what we need right now. And then that is where we discussed my research project. So just to end with this, I want to tell you guys some ways you can protect your family and yourself from PFAS. So the first thing you can do is try to minimize your intake of fast food. I think here in Monteverde, I've never seen a fast food restaurant, so you guys are already like one step ahead. But in the US, we have fast food on every single corner. So just try to minimize your intake of fast food, and you can protect yourself from PFAS exposure. Now, a lot of us have the non-stick cookware, and a lot of people think they have to throw out their pot or pan to save themselves from PFAS. But the truth is, you don't have to do that. As long as you don't heat your pan above 260 degrees Celsius, that's about 500 degrees Fahrenheit, then you won't have to worry about PFAS getting in your food. If you reach this temperature, that's when the PFAS actually separate from the pan and they're going to go into your food. But I don't really think anyone ever cooks food in a pan above this temperature, so all of you should be safe with your PFAS non-stick cookware. Also, anytime you have to buy new rain gear, new camping gear, new shoes, new clothes, cosmetics, beauty products, any of that, you can go online and you can read about if they have PFAS in their products. There's a lot of great websites that will show you PFAS-free brands. And if you want to know some of those, you can talk to me after and I can share those with you. And then lastly, if you have the ability to filter your water using those special filter pitchers, that's also a great way to just filter out some of the PFAS that's in your tap water. So with that, I would like to thank Central Chemicals Incorporated, the National Science Foundation for sponsoring my work, and then the supercomputer that I use at Michigan Tech. And with that, I will take any questions. Yes?
Do you think if we boil the water, the tap water, instead of using the filters, would that work?
So unfortunately, boiling our water will not work. PFAS are resistant to heat, so boiling it won't break down the contaminant. Boiling might release your PFAS into the air as a vapor, but in the end, you're either going to inhale it or it's going to go back into the water. So I wish boiling would work, but it does not. Yes?
If you find out that the UV technology works, how would you apply it in the field without affecting other things?
Yeah, that's a really good question. So one of the challenges was we wanted to find a technology that would destroy the PFAS, but we didn't want it to be some brand new technology that would cost us billions of dollars to implement into water treatment systems. So luckily, in a lot of the treatment systems in the United States, we already have UV lights installed. We have UV photoreactors because we use UV light for disinfection to kill off viruses. So we already have the technology in place. We would just have to add that salt, that sodium sulfite, to those photoreactors to create those electrons and destroy the PFAS. Yes?
Thinking about the applications of your research, it seems really clear that it could be really helpful for managing the PFAS that are already in the environment, but I'm imagining it also should be informing the companies, DuPont, that are creating it and helping us understand whether there are some choices we can make to use certain PFAS that meet our needs, our product needs as humans, but don't create so much damage in the long run. You see that as part of the application?
Absolutely. You know, we can't just keep mopping up the spill. We have to turn off the source. So what a lot of companies are doing now is it's out in public now. It's in public that these are toxic chemicals and people are starting to shun companies that are using PFAS. And a great example is actually 3M. These are one of the biggest producers of PFAS right now. So that's kind of scary. But what these companies are doing is they're slowly phasing out the use of PFAS compounds. So you guys saw in my presentation the two main PFAS, PFOA and PFOS. These are no longer being produced by any manufacturers in the world because of how toxic they are and because of how persistent they are in the environment. So those are being phased out, and these manufacturers are working on phasing out other PFAS compounds. They're also looking at if they can just make shorter chain PFAS and seeing if those are going to be less toxic to humans. It's actually really funny you brought this up because Paul, he is taking an electronics class right now, and they're using PFAS chemicals in their circuit boards. So Paul actually reached out and he's like, hey, these are really toxic. Is there anything we can do to avoid using these in our circuit boards? So currently his class is looking into different substitutes for that material. Or something along the lines. Yeah, Paul knows better than me.
I was having a conversation with representatives from the IPC. They're a group that makes standardized documents for how to make a circuit board. And the IPC is meeting with the EPA and trying to figure out the best ways to remove PFAS from the creation of circuit boards because it's a critical part of the lamination process in making electronics.
Hopefully that answers your question. Any other questions?
I just have a comment, it's so incredibly powerful that you can predict using the software that you're engaged with and the computers. Eventually there's going to be some hard data, right?
Oh yes,
and
lots of data.
Isn't that the ultimate goal? I mean, it's mind-boggling that you can do this, and get a result. get a predictable result,
Mhm.
where it's really not happening, but you're relying on that.
Yeah.
So with all of that, I'm wondering at what point do we have that correlation, on the graph that
Yeah.
says, you guys got to stop doing this because this is proof. I mean, that's what your goal is, I would assume, right?
Right, yeah. And, we have this really advanced software, but the question is how accurate are these values I'm getting? So I actually was able to validate all of my numbers using there's a little bit of experimental data on the PFAS, there's not much, but I was able to use that data to actually validate all my results. So we're getting to the point where, do we really need the lab anymore, or can we just use supercomputers?
Crazy.
It is crazy, yeah. Yes?
Where does your research fit in a larger body of research, like is National Science Foundation investing in an initiative, or are some of these companies like DuPont actually invested in finding better solutions?
Yeah, that's a good question. So I think the reason the National Science Foundation chose to fund this project was because they need a lot of people working on the PFAS issue. And there are a lot of water treatment systems who actually, this is kind of funny, but they will call my advisor and be like, do you have a solution yet for the PFAS? So there are, water treatment plants, there's manufacturers just waiting for this technology to become readily available so they can start applying it right away. Other questions? All right, well, thank you so much for